So that takes us on to today's topic, large panel system structures. So what are LPS structures? As a bit of a backstory, in the 1950s, many local councils across the UK struggled to meet demand for social housing, and this was a difficult time post-World War II. And as an industry, we needed to put our heads together and think of a quicker way of constructing our social housing. One of the quicker methods was fabricating standard panel systems off of site and then assembling them into multi-story structures on site. It was a quick process, and the panel quality could be closely monitored in off-site workshops. There were some leading manufacturers of these systems, which were Bison, Larson, Nielsen, Taylor, Woodrow, Anglian, or TWA, Camus, Jefferson, and Waits as well. The concept is illustrated on the screen that you can see there. So we've got large panels which are put together with some in situ stitching between them. The system is a gravity-based system. It relies on the panels being tied together by the use of hoops, as shown there. The overlapping hoops that the project from the panel extremities are then linked together with dowel bars, and then they're cast in little in situ grout slot or concrete slot. And as you can imagine, if these loops were missed, then the structure is considerably weakened because they're not tied together. And then what's worse is that that missing loophole is masked by the concrete strip that you've just installed, so you can't actually tell until you break it out mechanically and actually have a look in there. The photo on the right, you can see that's what a typical LPS structure looks like. We can see large panels with windows in there, residential. It's in a grid arrangement. It's tall, rectangular shaped building. This suggests it's an LPS structure just from looking at it. Doesn't mean it is one, but it gives you a good idea that it may well be. So what are the associated risks? The risks on these buildings are similar to other structures, but the risk is magnified due to the construction type. So we're talking risks such as fire, gas explosions, accidental impact loadings, or just generally overloading the structure. All these can happen to any structure, but an LPS structure are particularly sensitive to it. And this is due to, and this is the big one, the disproportionate collapse mechanism, or pancake collapse mechanism. An example of this collapse is shown on the left at Ronan Point, a famous case study. A localized failure that resulted in the collapse that caused kind of all through the structure, as was shown there, disproportionately. The Ronan Point collapse, that was in 1968, and it was reported that there was a gas explosion that caused the panels to fail in one apartment, which then resulted into the collapse of several stories of the structure and resulted in 4 deaths. It's commonly recognized that the Ronan Point failure resulted in the introduction of the disproportionate collapse or damage as a structural concept, and then led to widely debated changes in the UK building regulations too. It's also absolutely key consideration during demolition works. It's worth noting that the legacy of the Ronan Point collapse included the building type being put into its own risk class, obligations on owners of the buildings to investigate and then strengthen the structure, as well as the amendment to design codes and building regulations as well. It's a serious issue that requires some serious consideration. And we can't afford for a failure like this to happen during demolition unless there's a suitable exclusion zone in place. So if you take one thing away from this talk today, it should be 2 thoughts, or I suppose risks, that should cross your mind on these structures, and that's latent defects and disproportionate collapse. Latent defects, that is a fault that could not have been reasonably spotted during an inspection. These can become a problem during progressive demolition, i.e. don't assume that something is there when it may well not be. And then disproportionate collapse is the disaster you can see there at Ronan Point, something relatively localized, leading to a large-scale collapse. And the legacy of these structures continues. Barton House in Bristol, a large panel type structure that was evacuated in 2023, and following surveys that concluded that it could collapse in a similar way to Ronan Point. So we still have got these structures that need to be, the risks need to be controlled. So what do we do with these risks? There are several methods that are commonly employed to mitigate the risks, and that's exactly what we're going to cover today. So on the whole, it is to have two things: a very in-depth understanding of the structure, which is garnered from a desktop study and intrusive site investigation. And for the demolition wise, it's the temporary works designed to eliminate risk from both overloading the structure and structural instability. And if we can't eliminate it, then we're going to reduce it as much as we possibly can. With regards to LPS structures, we've got extensive experience at Andon in preparing demolition reports, advising on demolition methodology, and preparing temporary works in connection with the demolition of high-rise LPS structures. Previous projects have included demolition on deconstruction or deconstruction strategies, which include three principal methods. One, deconstruction with cranes. So removing the structure top down with either a crawler crane or a tower crane, panel by panel. Second one is ultra high reach demolition. So using an excavator with a really long arm, removing the structure top down from ground level. A couple of images shown there. And then the other one is a top down demolition in situ. So using small plant on the structure, removing the structure mechanically floor by floor, taking it down to the lower levels. And on many occasions, a combination of these techniques may well be used depending on the structure layout and demolition methodology chosen. So we'll start with deconstruction with cranes. Usually a tower crane or a crawler crane, as I've said, and it's a very controlled method that mimics the construction method that was commonly used to build these structures. Each panel is supported by removing, using the panel by the crane and then lifting it to the ground for further processing. Small excavators are often used to sit on top of the floors to mechanically persuade panels to break free from the structure. And then the propping to the panels is required to ensure that the panel remains stable just prior to lifting and taking weight with the crane. We've got some examples shown here. A key risk to this type of methodology is the crane itself. When a crane of these sizes that are required here, when they collapse, that always makes the headlines, and for good reason. They typically have a large collapse radius. And then there's also a risk of the crane being winded off, which can have quite large time and cost implications on the project too. Cherry Tree Court. It was an LPS tower deconstructed with a tower crane by P.P. O'Connor in Manchester and Salford. And just the look of the building suggests that it's LPS, and then there was also quite intrusive investigations that we carried out to verify its structural form, and you can see that they've got strengthening brackets on some of the panels that were installed as part of the review of all the LPS structures to make sure that they were in suitable condition for occupancy. So there was a top-down removal. We've got panel propping here to enable the removal of the head restraint. So the panels are propped, and then you can take the slabs on the top off, because remember, the panels, they require that head restraint to remain stable. So if you're removing that head restraint, you need to put some props in there to ensure stability. And then we've also got a lifting arrangement of the panels, taking them down to the ground for mechanical processing with a demolition spec excavator. And then we lift them up, and we can see there we've got the wall panel being picked up and removed, and floor panels picked up and removed there as well. This process continues to around about floor 3 or 4, at which point the rest of the structure is mechanically demolished using a large excavator operating at ground level. Using a high reach excavator is a great way to remove people totally from the building during demolition, which eliminates the risk of any operatives being inside a partially demolished structure. And this is because that the ultra high long reach excavators are used to carry out the works operating from ground level outside the structure extents. There does remain a risk, however, which is a risk of fly. Or a fly or ejector is small bits of concrete debris that are projected out from the structure during demolition. And that can happen when the crushing jaws of the excavator attachment are cracking the concrete, and then little bits of concrete split off, being fired out into all different directions. And the best solution here is to have a large enough exclusion zone so that we can make sure that the trajectory of those bits flying off land within sites. But that's not always feasible or available. So that we can employ solutions such as screens to mitigate this risk, as a relatively small example here, which we've used on a job, but larger ones can be used. Or an alternative method is to use a demolition curtain slung from a mobile crane. So we've got a project in Edgbaston shown here that was carried out by DSM, and that was carried out using a long reach excavator and a debris curtain hung from a crane. So you can see there that they're taking out the panels bit by bit and removing the debris from the floor as they come down. You can see that the crane, the mobile crane, kind of jumps here and there, protecting certain elements of the sensitive structures as it may need after demolition progresses. The methodology here is we're working towards the core of the building, which provides the stability of the structure, and so the rest of the structure has been stripped, and then we're working on the core, working down there, as we can see. Controlled, progressive. There's no one in the building. Still, fingers all the way at the floor. And finally, top-down demolition in situ. The purpose here is to lift small plant onto the roof and then remove the structure panel by panel, floor by floor, until the structure is again about 3 to 4 stories high, at which point an excavator can mechanically remove the remaining structure from ground level. And this leads us to our case study today, which is on Coventry Point, which is those 3D images shown there. So this project includes the top-down demolition of 2 linked large panel system structures. They were slap bang right in the middle of Coventry city centre. The client was Coventry City Council. The principal contractor was Coleman and Company, and I was the lead temporary works engineer and temporary works supervisor on the project too. I worked closely with the site team, regularly visiting site and carrying out investigation works and various inspections and reports. The building was a local landmark that was being cleared to make way for the council's plans to regenerate the city centre. And then the ground level of the building, what was there at the point, but just before closure, was a series of restaurants and shops, and then also around the perimeter of that area, lots of shops as well. So it's quite a busy area, a thoroughfare going through this part of Coventry. There was also a link bridge that led from one of the towers to a multi-storey car park. As you can imagine, the quite considerable constraints associated with this in the public and the shops and the buildings, and not forgetting that it's an LPS structure. So we've got a 3D illustration here of the general sequence of the top-down in situ demolition. Plant is lifted up to the top floor, the structure is demolished floor by floor until the whole thing is no more. There's a typical methodology for most top-down demolition methods, really, and the difference with this structure is that it was LPS, so there was additional measures and temporary works that needed to be considered. So to facilitate the demolition works, there were several temporary works items that were required, and these were the global stability assessment of the structure coming down, comprehensive site investigation review, and a desktop study, which included speaking to Bison, who were the manufacturer of the panels, just for some insider information and details on the pre-stressing techniques and typical pre-stress values that were used at the time, or to assist in that structural assessment of the building during demolition. Sequencing of the demolition, precast panel stability works, including the propping design, plant justification, link bridge demolition, and then also the scaffolding checks and the hoist checks Some of these items are relatively self-explanatory or typical for other top-down schemes, such as the scaffolding and hoist, etc. But I'm going to focus now on the design items that are associated with the LPS structures and the risks that are associated with those structures too. So first risk, number one, we need to understand what exactly that we're working with here. Extensive site investigation is required to ensure we have a good understanding of the structure. We worked hard with Coleman's to establish a robust schedule of investigations. Then this investigation scope would hopefully identify how well the structure was put together, i.e., was it built by a Fred in the shed type company who just threw it up in no time at all, and thus leading to missing loopholes and latent defects, etc., or was it really well constructed and properly constructed? In this case, the structure was actually constructed really well. There were no instances where the panels failed prematurely due to any latent defects. The plan of the site investigation is shown here, and we provided details of exactly what we were after. We wanted to take a reasonable sample of the structure so we could get a representative feel for the building. And we've got the underside of some of the floor planks here showing the pre-stressing strands, which were in the bottom and the top face. But there's also concrete infill near the end of the panel supports. This is typically done to increase the shear resistance of the panel where the shear loading is usually highest at the supports. That white stuff there is insulation, which were formers to provide voids. And then here we've got the panel to floor connection. And you can see that the loop has been captured with a dowel, which is exactly the kind of thing that we're looking for. So this was the structure stood down at street level, and you can see that's really high when you stood right at the bottom there. It's one of the elevations that face the high street, and the scaffold would encapsulate that whole structure. But, and this is kind of risk number two, how do we prevent panels becoming unstable once they've had their head restraint removed? The wall panels rely on self-weight at the floors above to maintain stability. Therefore, as this is removed progressively during demolition, they need another support system in place. And on this project, we utilised simple raking props, which were bolted to the wall and the floors. And we also had a little tension tie lower down to prevent the panel from kicking out at floor level, which is like a 1.5 ton safe working load ratchet strap in this case. This system ensured that the panels would remain stable during both the demolition of the floor slab as well as during the demolition of the wall itself. So that deals with the big stuff. The large panels aren't going to go anywhere. How do we stop the smaller debris leaving the site perimeter? High up on the high street, it's really important to prevent small bits of concrete or scaffold clips or tools falling, as this can fall to the ground with a tremendous force from that height. So you can see some simple methods of achieving this. We've got screens to deflect material back into the building, which work well, and the beams over the windows as shown here. But another method was to encapsulate the scaffold with that is sheeted, and also had demolition fans as well, which essentially captures items from during the construction of the scaffold, the demolition works, and during the striking of the scaffold too. The scaffold was also detailed to have a 4mm ply screwed down to the working level at the top, which prevented small debris falling through the scaffold as well. Another protection measure that was employed was to construct a proprietary deck in the area that was closest to the tower and quite a busy walkway. As this was a key kind of thoroughfare through, we encapsulated that whole area in a deck along that walkway, and a combination of all these methods working from the source where the plant is down to the crash deck just above the public mitigated the risk of falling objects and ensured the safety of the public. Now that covers protection methods that protect the public should any material leave the top of the tower. But you may be thinking, isn't that more of a reactive method that doesn't really focus on the source? That's kind of a reactive response. So the most effective method of reducing risk, as we know, is, well, not really reducing it at all. It's totally eliminating that hazard. In this case, the hazard was the demolition works, which we couldn't really eliminate that. And so we had to carry out the demolition at times when there's no public around. And this solution was risk zoning. So we identified red, amber and green zones according to the risk that was associated with that particular area. And the red ones were carried out outside normal shopping hours, whereas the amber and green were carried out in the day, providing that the planned exclusion zones in the public zones were adopted. So the best way to reduce risk, as we know, is to eliminate it. And that follows the ERIC principle of risk reduction, which is the eliminate, reduce, inform, and control. So the risks are mitigated, and then now it was a case of carrying out the works as planned. Here's a photo of the structure as it's on its way down, getting shorter and shorter, floor by floor. I took this photo from the car park, which was opposite, and you can see that you've got the monoflex structure there, the demolition fans, and the structure is getting shorter and shorter and shorter. And then that's it. That's the job complete. The picture illustrates that large mushroom that was at the 3rd level podium on one of the towers, and this was removed mechanically using large excavators at ground level. So to summarize, the key challenges were in reducing risk, the structure being LPS, and the proximity to the public. This project was successfully completed, and I haven't been back to Coventry city centre since, but I'm not sure what it looks like now, but it is without 2 large LPS towers, let's put it that way. Okay, on to another case study then. So this case study is the justification of plant to operate on Hartop and Lannoy Point towers. The structure was LPS structure and also had small floor spans, which led to a problem in justifying the plant and associated demolition loadings on the structure. The small span and lightweight floors that are pre-stressed are quite difficult to prove in theory when there's no information on the pre-stressing forces. So the pre-stressing forces provide a significant strength to the slab. So not knowing what that is becomes quite problematic. So on this project, as the floors of the structure were made of precast and pre-stressed concrete panels, they had small spans, and there was some uncertainty about the interaction between the 2 panels and the load. We didn't want that kind of piano key effect that you get if you've got 2 panels next to each other. We needed to complete a load testing scheme to verify that the 3-ton excavators that were required to carry out the works could operate on the structure safely. Following an initial analysis of the structure and our best guess of what those pre-stressing forces were and the live load capacity of the slab, we found that the worst case bending moments applied from the plant were when the machine was operating on its toes in the orientation as shown here in the middle edge of a panel. We also found that the worst case shear scenario was in the plant was on its toes operating as shown near a support, which is all pretty conventional and what we would expect. In order to complete the loading of the panel, we detailed a propping system that would then utilize the weight of the floors above to act as cartilage that we could then jack down from. And you can see that we've used some aluminium towers here that are braced together with ledger frames, and then they are back propped up the structure, utilizing enough of the vertical load that we can push down to sufficient force and therefore replicate the 3-ton loadings on that slab. This arrangement of using towers and using the structure above you isn't the only method. Another popular method is to use tension ties and rods to tie through underneath you. So you're using it's similar to this, but kind of mirrored. And then you're using the weight of the floors below to almost to pull down. Both of these methods use hydraulic rams as the loading ram to apply the load, which is an effective method because as soon as the structure moves, it will kind of unload itself. The alternative is to use a dead weight test, which you pile dead weight, so building blocks or water or something similar to the structure. But the difficulty with that one is that if the structure starts to crack and to fail, then you can't remove that weight. Whereas with these solutions, the structure almost unloads itself, so you don't get that potential catastrophic collapse through your slabs. The load is going from the load cell up through the props and up through the structure to mimic. That's what we're trying to do. We're trying to mimic that the worst case excavator loadings. So we've got the shear test arrangement here, and this is similar really, but rather than putting the force into the middle of the slab, we are putting the force towards the edge, and we're trying to mimic the load case where the excavator is in worst case shear. The difference here is that we utilize the load in the wall rather than the floors above only, so we could get away with slightly less propping work. So we've got section 3, the test setup was shown here. We detailed the work so that the engineer loading the structure and the engineer taking the readings can do this remotely from an adjacent bay in a place of safety. Although it's important to note that at no point here are we testing to failure. We're just testing to our best estimate of what we think the structure can do. And then the load is applied in increments, and we also allow a dwell time between each load increment. We're going to load the structure up to a maximum of 2 times the proposed loading, or a point at which the engineer on site deems that the structure is reaching its capacity. The structure will be continually monitored by the engineer undertaking the testing, and the deflection results will be plotted in real time against that load application, so that if there's any cracking or if there's any non-linear load versus deflection on our graph, then the engineer can terminate the test and can investigate. It's a robust method to ensure that the slab can't be overloaded. This is not an assessment method that should be carried out in isolation, and I need to stress that. It's not an isolated thing, we just carry out the load testing and that's it. It's important to carry out the desktop study and research and then the theoretical calculations beforehand, so that we've got a really good estimated, educated estimate of the structure's capacity before we start doing the testing. And then ultimately on this project, the testing proved acceptable and the works were able to proceed with the 3-ton plant. That's a couple of case studies focusing on large panel system structures. And to summarize on those structures and LPS structures, they are structures that must not be taken lightly. They can be demolished safely, providing suitable risk mitigation is considered during the design stage and then during the demolition works as well. And at Andon, we've got knowledge, experience and understanding of these risks, and have the knowledge, experience and understanding of that practical application of risk mitigation required to ensure a safe project. And that leads us to the end of our presentation today. So if you'd like to know more about this topic, LPS structures and temporary works and demolition in general, the BRE, they've got a great deal of information on large panel system structures, including registers of buildings that are LPS as well. And in terms of demolition, the National Federation of Demolition Contractors, NFDC, and the Institution of Demolition Engineers, IDE, they're also really great starts. The NFDC also have a guidance note on temporary works too, which I've shown a screenshot in there. In the wider field of temporary works, there is the Temporary Works Forum guidance on constructability of temporary works, as well as a lot of content on their website as well. There's a really great newsletter by Cross, which is a free resource that you can sign up to, and it gives you the newsletter through your emails. And it covers the confidential reporting of structural safety. It provides really quite helpful reports on modern issues in construction that may well be becoming more and more common or are trending, and you can look out for those in your particular project or on future projects. But it's a good way of that confidential hub of information, which then gets that learning gets distributed out to the industry. So it's a really good resource. There's also a very good book that I've noted there. So that's called Collapse: Why Buildings Fall Down, and that runs through a lot of case studies of former disasters that we can learn from. And then last but not least, there's the Andon webinars and YouTube channel, which I've screenshotted in there. So we've got 80+ videos on there, which provide some great CPD with all sorts of content ranging from complex demolition case studies to net zero challenges in the industry to crash course in plate bearing tests on working platforms.